This question is saying, let's calculate the maximum height above the ground reached by block A. It sounds like a typical vertical projectile motion, but it is way more than that. You're gonna see what I'm talking about when I answer the question. Can I even answer the question? That's the question on its own. Let's do 2.1 so that I can show you what I'm talking about. So 2.1, the question is saying that let's show by means of calculation that the magnitude of the acceleration of block B was 3.88 meters per second squared while the block was moving vertically downwards. So let's go ahead and read our question statement so that we can see what is going on. So when block B is released, so now we know fully well that this block B is released at some point. It moves vertically downwards and strikes the ground with a velocity of 3.41 meters per second. So if it is released, then we know that VI is equals to 0 meters per second. And we're given VF, the velocity at which it strikes the ground. It is said to be 3.41 meters per second. What else do we have? We have the distance or the displacement of our object B, right? From the time it is released to the time it strikes the ground. So we have delta Y being equals to 1.5 meters. And what are we looking for? We're looking for the acceleration, right? So based on the vertical projectile motion, you can see what we have to use here. VF squared is equals to VI squared plus 2a delta Y. We have VF squared, we have VI, we have delta Y. So we can use this formula for sure, right? It's gonna work because we're looking for the acceleration. So let's take direction towards the ground as positive. If we do that, then our VF is 3.41 squared, which is equals to our VI, which is 0, we square that, plus 2a, and then if we take in direction towards the ground is positive, then our delta Y will be positive 1.5. We're gonna have 11.6281 being equals to 0 squared is just 0, right? And then here we have 2 multiplied by a multiplied by 1.5. That is equals to 3a. So if we divide both sides by 3 in order to find our acceleration is equals to 3.88 meters per second squared, right? And that's exactly what we are asked to prove. So our answer for 2.1, we're quite confident we're doing the right thing. And then now 2.2, let's draw a free body diagram showing all forces acting on block B immediately after it was released. Right, so let's just go ahead and do that. So for block B, we're gonna have the weight pointing downwards, right? And then now we can start thinking about everything else. You know the weight is gonna be there, so you put the weight first, and then after that you have to start thinking about everything else, right? It is connected to a light inextensible rope, so we're supposed to have tension force going up, right? So we have tension and weight. We have two forces acting on the object, and the question also has 2 marks, right? So we're quite confident we were able to identify all the forces. If the question was out of 3 marks and we had only 2 forces, we were most likely going to be doing something wrong, right? You should be aware of that. And then 2.3, this is the one I want you guys to do. State Newton's second law of motion in words, right? We know that the acceleration is directly proportional to the F net, and so on and so on. Let's just do 2.4, right? Before doing 2.5. So 2.4 is quite an interesting one also. It's saying that let's calculate the value of M by applying Newton's second law to each block while they are in motion. People are getting this question wrong so often, such that they're telling you to apply Newton's second law in each block, right? They usually just say calculate the value of M, and you have to figure it out yourself that you have to use Newton's second law on both blocks. But then now they're actually telling you, let's go ahead and apply it on block B and see what's going to happen. So for block B, we have the free body diagram, right? So when I say F net is equals to MA. And then we're gonna say the force that is pulling the object minus the force that is opposing. The object is going down, right? So it means that we have the weight pulling our object, and then the tension is opposing. So we're gonna say that the weight minus the tension is equals to MA. So what is the weight? The weight is 7.5 multiplied by 9,8 minus tension is equals to the mass, which is 7.5 multiplied by our acceleration, which is 3.88. So what is 7.5 multiplied by 9.8? That is 73.5. And then minus tension is equals to 7.5 multiplied by 3.88. Which is equals to 29.1. So minus tension will be equals to, so now we take in this term here to the right hand side, so that it will be 29.1 minus 73.5, which is equals to minus 44.4, right? So if we divide both sides by minus 1, we're gonna get the tension being equals to 44.4 newtons. Right, we have the tension, but that's not what we're looking for. We're looking for the value of M, right? So now we have to go to that object. So for object A, still F net is equals to MA, right? There's no other way. So let's have a free body diagram for object A so that we can see what is going on. So for object A, the tension is pulling the object upwards, right? And the weight is opposing. So here we must have tension minus the weight, because now it is the tension that is pulling and the weight that is opposing, unlike in object A. Right, so the tension, we know that it is 44.4 minus the weight. The weight should be M multiplied by 9.8 is equals to the mass multiplied by the acceleration, which is 3.88. Right, so we're gonna have 44.4 minus 9.8 M is equals to 3.88 M. It's easy to see that we're gonna have 44.4 and then it's equals to, so we take in this term to the right hand side, so that is 3.88 plus 9.8, which is equals to 13.68 M. If we divide both sides by 13.68, we're gonna have 44.4 divided by 13.68, and then the size of our mass is 3.25 kgs, right? So we have our mass, the value of M, that is 2.4. And now 2.5, let's just do 2.5 real quick. So let me show you something. Let's calculate the maximum height above the ground reached by M. So initially I was thinking, why does this question have 5 marks? It should have 1, because from this point here to the ground it's 1.5, and then while B is moving from that height to the ground, then A will move from the ground to that height, which is 1.5. So the maximum height for A should be 1.5. Why does it have 5 marks? I don't understand. But then I realized that when it reaches this height, which is 1.5, it has a velocity which is not equals to 0, right? So it's still going to go up for some time, because its velocity there is not 0. So it's not stopping. It's still going up until it ultimately gets stopped by gravity. Right. So what is the velocity at this point? That is the question we are interested in. The velocity at that point is equal to the velocity that the object B strikes the ground with. Right. And then what is the value of that velocity? That is 3.41. It is given to us here. So at this point here, at this height, ball A has a velocity of 3.41 meters per second. I was not so sure about the velocity of A at that point. I actually calculated it, and then I realized that, okay, fine, the velocity at which ball B strikes the ground with is the velocity of ball A at that height, because the acceleration is the same, and then VF is not dependent on the mass. When we're using VF squared is equals to VI squared plus 2A delta Y. So we have the velocity at that point. We want the maximum height above the ground, right? But then another thing we have is VF, right? Which is at the maximum height we're interested in. That VF is equals to 0. Because at that point, your object will no longer be going up. So if we find this height here, and then we add it to the 1.5 we have, then we have the height of object A above the ground. So let's go ahead and do that. We're saying that VI will be equals to 3.41 meters per second, and VF will be equals to 0. Right, our acceleration, how much will our acceleration be? If we take upwards is positive, our acceleration will be minus 9.8 meters per second. That is because when ball B strikes the ground, object A will now be in free fall. The tension force on that rope is going to be equals to 0. Right, so we have VI, we have VF, we have the acceleration, we want delta Y. Right, so it's easy to see now that we can say that VF squared is equals to VI squared plus 2A delta Y. So VF is 0, maximum height, and then VI, if we take it up as positive, that is 3.41 squared plus 2 acceleration minus 9.8 because we're taking upward as positive, and then multiply by delta Y. So we have to take this term to the left hand side. So 3.41 squared is equals to, so 3.41 squared is equals to 11.6281, right? If we take it to the other side, we're going to have minus 11.6281 being equals to 2 multiplied by minus 9.8, that is minus 19.6 delta Y. If we divide both sides by minus 19.6, we're going to get 0.59. So 0.59 meters is equals to delta Y. So here we have 1.5, and then here we have 0.59. So our height above ground, is 1.5 plus 0.59. Right, that will be our height. That is equals to 2.09 meters. Free fall is the motion of an object where the only force acting is gravity. Right, so that is 3.1. Let's go ahead and do 3.2.1. So the question is saying that let's calculate the time taken for ball A to strike the ground. So let's look at ball A here. It is released from a height of 15.2 meters above the ground. When it is released, we know fully well that VI is equals to 0 meters per second. Right, and we have delta Y. So let's take up as positive. If we take up as positive, then delta Y should be equals to minus 15.2 meters when our object strikes the ground. Another information we have is the acceleration, as we always do, minus 9.8 meters per second squared. And what are we looking for? We're looking for the time it takes the ball to strike the ground. Right, so based on the variables we have, VI, acceleration, delta Y, and the time that we're looking for, it's easy to see now that we're going to say delta Y is equals to VI delta T plus a half A delta T squared. Right, initially I didn't want to use this formula because what about delta T squared and delta T? I'm going to have to solve this by factorizing, right? But then I realized that VI is equals to 0. So this term here is going to give me 0. I'm not going to have so many issues, right? So if we go ahead and substitute we're going to get minus 15.82 is equals to VI, which is 0, right? Multiplied by the time. So that term falls away. Plus a half. The acceleration is minus 9.8 and the time is what we're looking for. So we're going to have minus 15.82 being equals to, this term falls away. We just have minus 4.9 delta t squared. So it's easy to see now that delta t will be equals to the square root of 15.82 divided by 4.9. Right, so now it's just a matter of putting that in your calculator, and what am I getting? I'm getting 1.76126 seconds. So that is the time it takes ball A to strike the ground. Right, it makes sense because it's gonna take about 1 second to cover 9.8 meters, right? And then the rest of the height can take less than a second, right? Let's do 3.2.2. So in 3.2.2, quite demanding one, right? 5 marks. We're looking for the magnitude of the velocity with which ball B was projected from the ground. So let's look at the information we have. We don't have VI. If you take the motion from the time it was projected to the maximum height, you can say you have a VF, which is equals to 0, right? But we don't know the maximum height also, because at this point, what we have is the initial velocity, which is unknown, and the acceleration, which is minus 9.8 meters per second squared. And then another thing we can calculate is the time for the motion of ball B, right? Because we are told that ball A and ball B, they strike the ground at the same time. But then when ball A was at this point, that is only when ball B was projected upwards. So we can say that the total time of ball A minus the time taken by ball A to go from maximum height to 3.2 meters below the maximum height will give us the time for ball B. Right, so let's go ahead and do that. So for ball B, not ball B but ball A, we can say that delta y is equals to vi delta t plus a half a delta t squared. Right, so now our delta y, we can say that is minus 3.2 meters because we're looking for the time taken for only this journey. That is the time we're interested in, right? We're going to subtract it from the total time, and that will be the time for ball B. Right, so if we substitute minus 3.2, then our VI 0 delta t plus a half minus 9.8 delta t squared. Right, so we're gonna have minus 3.2 being equals to minus 4.9 delta t squared. If we make delta t the subject of the formula, we're going to get 3.2 divided by 4.9. We know that minus and minus, they're going to cancel out, right? And our time will be 0.8. So we have 0.8081. So right, the time for this part of the motion from this point to this point is 0.8081. Right, so to find the time for the entire motion of ball B, we can say that so the time for ball B, we're going to say that it is equals to the total time for ball A, which is 1.76126 minus 0.8081. Right, so let me just put that in my calculator real quick so that I can see what I get. I'm getting 0.95316 seconds. Right, so that is the total time for ball B. Let's revisit the information we have for ball B and see if we can manage to find that VI. We have the time for the total motion. Right, we can put that in mind. And then VI is still our unknown. We have the acceleration, which is minus 9.8 meters per second squared. But if we take the motion from the ground to the maximum height, we can say that we have VF, right? We have a VF which is equals to 0. And then to find the change in time from ground to 0, we're gonna say total time divided by 2, because the time taken from ground to the maximum height shall be the same time from maximum height to the ground. It is actually wrong for me to put this dot here. We don't know how high ball B is above the ground at maximum height, right? So if we divide that total time by 2, so we have 0.95316 divided by 2. Let me just put that in my calculator real quick. I'm getting 0.47658. So now I have delta T. I have delta T. I have VI is what I'm looking for. I have acceleration. I have VF. So it's easy to see now that I can say VF is equals to VI plus A delta T. VF is 0. VI is what we're interested in, plus our acceleration, which is minus 9.8 multiplied by the time, which is 0.47658. So minus VI is going to be equals to, so I have minus 9.8 multiplied by 0.47658. Right, so I get minus VI being equals to minus 4.6705. And then VI is equals to 4.6705 meters per second. Right, that is the initial velocity for which ball B is projected upwards. Now the last question, 3.3. So on the same system of axis, let's draw the position time graphs to show the motions of both ball A and B from the instant ball A is dropped until the time it reaches the ground. Let's take the ground as the 0 position, right? Because usually they will say let's take the ground as our reference point, and that will lead to a lot of ambiguity. What do they mean? You know, reference point. Are we taking it as 0? Are we? What is happening? But then when they say we must take it as the 0 position, that is clear. There is no ambiguity. You know exactly what is expected of you. Right. So the x-axis, there we go. And then obviously on the x-axis, we're going to have the time in seconds. And on the y-axis, we're going to have delta y in meters. Maximum height 15.2. So let's start with ball A, right? So ball A is starting from 15.2 and then it goes down until it strikes the ground, right? It takes 1.76 seconds for that motion. So we have 1.76 seconds, right? And then now we have to go to ball B. So ball B is only projected 0.8 seconds later. So we have 0.8 here, right? Yeah, that is the time at which is projected. And then it goes up to its maximum height, which is less than that of ball A. That's, yeah, it's easy to see. But then they strike the ground at the same time. So I think we should have something like this. I wonder what you guys did. Can you please let me know in the comments if we have the same position time graph? The total linear momentum in an isolated system is conserved. That is the principle of conservation of linear momentum in what? 4.1, right? So let's go ahead and do 4.2 and see what is happening here. So the first question, 4.2.1, calculate the magnitude of the velocity of the trolleys immediately after the collision. So based on the principle of conservation of linear momentum, we know that the sum of the momentum before should be equal to the sum of the momentum after, right, if that system is isolated. So for our case here, we have trolley A, which is moving to the right, and we have trolley B, which is stationary. And after they collide, they move together as one unit, right? So if we set up our equation here, we'll get m1 multiplied by the velocity plus m2 multiplied by its velocity, being equals to m1 plus m2 multiplied by Vf. If you're confused and you can't see what is happening, that is because the momentum is equal to the mass multiplied by the velocity. So this right here is the momentum for trolley A, the momentum of trolley B, and the momentum as they move together as one unit. Right. So if we go ahead and substitute, we're going to get 7.2 multiplied by 0.4. We take in direction to the right is positive, right? Plus the mass of trolley B, which is 5.3 multiplied by 0, right? It was stationary, and then this will be equals to 7.2 plus 5.3 multiplied by the final velocity, right? So if I put 7.2 multiplied by 0.4 on my calculator, I'm getting 2.88, and 5.3 multiplied by 0, that will just be 0, right? And that will all be equals to, so now I have 7.2 plus 5.3, which is 12.5. So I have 12.5 multiplied by Vf, right? It's easy to see now that I just need to divide both sides by 12.5. So if I divide both sides by 12.5, let me see what I get. I'm getting 0.2304 meters per second, being equals to Vf. So there we go. I have the final velocity of the trolleys immediately after the collision. Right. And 4.2.2, let's calculate the magnitude of the average net force exerted by trolley A on trolley B during the collision if the collision time is 0.02 seconds. So there's two ways of doing this one. You can say that F net is equals to the change in momentum divided by the change in time, or you can say that F net is equals to the mass multiplied by acceleration. They're all going to work, but let's just use the first one, right? If we use this first one, we know that the change is equals to the mass multiplied by Vf minus Vi, right? We're on the same page now. We can go ahead and substitute. So F net will be equals to the mass. So let's use trolley B, right? You can use trolley A. You're going to get the same thing. If we use trolley B, we're going to get the mass being equals to, what is the mass again? 5.3. And then Vf is 0.2304. And then it's coming from rest. So its Vi must be 0. And we're dividing all that by 0.02. That is the amount of time the collision took, right? And then putting that in my calculator real quick, I'm getting 61.056 newtons. It is a force in which the work done in moving an object between 2 points is dependent on the path taken. So that is 5.1, a non-conservative force. right? And then 5.2, let's use energy principles to calculate the speed of the crate when it reaches point C. Right, so let's see what's going on here. We have an electric motor that pulls a 20 kg crate from rest at point A, right, up the incline by means of a light inextensible rope. And then we can see that the incline makes an angle of 18 degrees with the horizontal B, C, and D are points in the incline plane. And then we can see clearly that the distance between A and B is 15.6 meters. Right, we are told that the motor exerts a constant force of 96.8 newtons parallel to the incline. And then there's a constant frictional force of 13.5 newtons. Right, so we're supposed to use energy principle. If the question says use energy principles, you can use work net is equals to the change in EK. Right, you can also use the work done by non-conservative forces equals to the change in EK plus the change in EP. Right, you can do that. So let's just go ahead and solve it using the first formula, right? I've actually solved it using both. So if you try this formula, it should also work. Right, so if we use that formula, we're going to get F net multiplied by delta x multiplied by cos of theta when it goes to half mvf squared minus a half mvi squared. Right, so now we can find F net so that we can find VF ultimately, right? So how can we find F net? Let's draw a free body diagram of the 20 kg block as it moves up the incline, right? So we have FG parallel, which is pushing the object down the incline. We have the frictional force, right? And then the force applied by the electric motor. We have the normal force, obviously, and we have the weight perpendicular, right? The normal force and the weight perpendicular are not going to do any work on the object. So we are interested on the force applied by the electric motor, frictional force, and FG parallel. So if we find the net force there, we're going to get the net force being equals to the force applied, which is 96.8, right? So we're going to have 96.8 minus the forces that are opposing, frictional force, that is 13.5, minus FG parallel. So FG parallel is mg sine of theta, right? So that is FG parallel. And then if we substitute that in our equation, the mass is 20 kgs, the acceleration is 9.8, and then multiply by sine of 18 degrees. So if we put that in our calculator, then F net should be whatever we get there, right? So let me just do that real quick so that we can see what we get. And then I think our F net should be equals to 22.7327 newtons. Right, so now we have F net, we can put it in our equation. So in place of F net, we now put in 22.7327, right? And then in place of delta x, we have 15.6. And then the object is moving up the incline, and the F net is also pointing up the incline. So the angle in between those two should be 0, right? So we're going to have cos of 0 being equals to a half. The mass is 20 kgs multiplied by VF squared minus a half 20 velocity initial. Our object is coming from rest, right? So multiply by 0 squared. Right, so let me just solve the left hand side. And 22.7327 multiplied by 15.6 multiplied by 1. What am I getting? I'm getting 354.6301 is equals to, so I have multiplied by 20, that will be 10, right? And then we have VF squared, right? So if we apply a bit of algebra here and make VF the subject of the formula, we're going to get the square root of 354.6301 divided by 10. Right, so now what is left, I just need to put that in my calculator, and our VF is 5.96 meters per second. Right, that is 5.2. Right, let's move to 5.3. So 5.3 is saying that let's calculate the minimum average power dissipated by the electric motor to pull the crate from point A to point C. So if we want to find the power, it's either we can use the work divided by the time, or we can use the force multiplied by the average velocity. Right, we don't have the time as it is, right? Maybe we can try calculate the work, but we don't have the time. But then if you look at the other formula, we have the force, right, that is exerted by our electric motor, right? And then we have VI, which is equal to 0, and we have VF, which is equal to 5.96. So we can add those two and divide by 2 to find velocity average. Right, so what am I saying? I'm saying that the power will be equals to, so the force that is exerted by our motor, that is 96.8 multiplied by velocity average. So I'm saying to find velocity average, I'm going to say VF plus VI divided by 2. So what is VF? VF is 5.96 and then plus 0 divided by 2. Right, so that is 96.8 multiplied by 5.96 plus 0 divided by 2. And then the answer I'm getting here is 288.46 for, what is the SI unit of power gain? I think it's watt. Right, so we're gonna have that there. I'm so much interested in how other people solved this problem, so please just let me know in the comments what you did for 5.3. Then 5.4 is saying that when the crate reaches point C, the rope breaks. So our rope is breaking at this point, at C. And then what happens next? The crate continues moving up the inclined plane, as you would expect. It comes to a stop at point D, and then slides down the plane past point B. Right. Draw a labeled free body diagram for the crate as it slides down the plane past point B. Right, so it's sliding down, and we need to draw a free body diagram for that motion. So when it is sliding down, FG parallel is still down the incline. FG parallel is down the incline. And then the frictional force is now up the incline. Right, and then we have our normal force there, and we have our weight perpendicular, or FG perpendicular, right? So I'm expecting 1, 2, 3. I'm expecting this question to be out of 3 marks because we have identified 3 forces, right? And indeed it is, right? So now I'm convinced that I have the correct free body diagram because my number of forces correlates with the marks for the question. Right, and then 5.5, let's look at what 5.5 says. So in 5.5, let's do a velocity time graph for the entire motion of the crate, starting from point A until it passes point B, and again on its motion down the inclined plane. Right, well, so we studied that V is equals to 0. And then at point B, we have, not at point B, but at point C, we have a velocity of 5.95 meters. So let's write 5.95 here. And then, right, let's have our VT graph. Yeah, so there we go to 5.95. And then what happens after we reach a velocity of 5.95? So the rope breaks, and then when the rope breaks, we no longer have that force that is pulling our object, but then our object will go up for some time before it reaches a VF of 0, right? As it is going up, its velocity is decreasing until it reaches 0, right? So let's see if we can indicate that in our graph. So it decreases until it reaches V is equals to 0, right? That is, now we add point D. We have reached V is equals to 0, because it's going to be increasing bit by bit until we reach V is equals to 0. And then after that point, now it is going down, right? Our object is going down and its velocity is starting to increase, right? So I'm thinking that we're going to have, yeah, something like this. Its velocity is starting to increase now. All right, so I'm thinking we're gonna have something like that until we reach point A again. We don't know the velocity of point A. I don't think we need to indicate the value anyway. Right, I'm quite interested on how yours look like. Can you please just let me know in the comments if we have anything similar? One of the most interesting questions under Doppler effect I've came across, that is 6.1.2, right? So let's look at 6.1.1. You just need to state the definition of Doppler effect in words, right? I'm sure you can do that. Let's look at 6.1.2, the interesting question. So the question is saying a car moves at a constant velocity of 22 meters per second on a straight horizontal road towards a stationary device, which can both emit and detect sound waves. The device emits sound waves with a frequency of 24,000 Hz. Alright. And then these sound waves are reflected off the car, and the reflected sound waves are then detected by the device as shown in the diagram below. We can see what is happening there. And then if the speed of sound in air is 340 meters per second, let's calculate the frequency of the reflected sound waves detected by the device. So let's do a bit of conceptualization here. So let's put X as our vehicle and put our device somewhere here. So the first thing that is going to happen, our device is emitting a sound wave, right? So let's just denote that. So we have some frequency of source, and then when it strikes the car, it's no longer Fs. We now have FL, right? It's going to is going to detect a totally different frequency. And then from that frequency it detects, it's now going to reflect it and send it back to the device. So now we have this frequency being reflected back to the device. And then now we have FL2. So you can use this Fs here to find FL, and then when you find that FL, it now becomes your Fs that the device is going to detect. Am I making any sense? Let me show you what's going on. So for the first part, we have the frequency of the listener being equals to V plus or minus the velocity of the listener divided by V plus or minus the velocity of the source multiplied by the frequency emitted by the sound source, right? So the frequency observed by the listener, or the frequency that strikes our vehicle, it will be equals to 340, and then our listener or our vehicle is moving towards the device, right? So we're supposed to have plus the velocity of our listener, which is 22 meters per second, and then we can divide everything by 340 plus or minus the velocity of the device, which is 0, right? It is stationary, and then we can multiply that by the frequency emitted by our device, which is 24,000. Right, so let me just compute that real quick. So I have 340 plus 22 divided by 340, essentially multiplied by 24,000, and I'm getting 25,552.94 hertz. So this is the frequency that strikes our car. This is the frequency that strikes our car. And now this frequency is reflected back to the device as FS, right? This frequency now becomes our FS, is reflected back to our device. So what am I saying? We're saying that now we're going to have FL being equals to V plus or minus VL divided by V plus or minus VS multiplied by the frequency emitted by the source. So what is FL? FL is what we're looking for, the frequency that is detected by the device, right, after it has been reflected. Right, that will be equals to 340, and then now our listener is the device. We know that it is stationary, so we're going to have plus or minus 0 divided by 340, and then now our sound source is moving towards, it is the car, right? So we're going to have 340 minus 22 multiplied by the frequency of the source, which is what we calculated here, 25,552.94 hertz. That is the frequency that is being reflected by the car. This is the trick of the question. As soon as you can wrap your head around the concept, then you're essentially done. So multiplied by 25,552.94 hertz. I'm getting 27,320.75 hertz. Right, so that is the frequency of the reflected sound waves detected by the device. Right, and the last question, 6.2, the spectral lines observed for a distant star show that the star is moving away from Earth. Explain by referring to frequency how one can deduce that the star is moving away from the Earth. So here, I'm much interested in how you guys answered this question. So can you please just let me know in the comment section. What happens when you have a positive and a negative charge? Right, we have two unlike charges. They're definitely going to attract. Right, so the answer to 7.2 will be something like the following. We're supposed to draw the net electric field pattern due to the 2-point charges. And now 7.3, we need to calculate the magnitude of the electrostatic force that Y exerts on X. Right, so we have Y and X right there. So F is equals to K Q1 Q2 divided by R squared. So what is the value of K? K is a constant, right? So we have 9 times 10 to the power of 9. And then Q1, we can take X as Q1. But when you substitute, you don't put the negative sign, you just put the magnitude, which is 7.2 times 10 to the minus 9 multiplied by Q2, which is also 7.2 times 10 to the minus 9. So we can just say 7.2 times 10 to the minus 9 squared, right? And then divided by the distance between the two charges. So we have 0.03, and then we can square that. 5.18 times 10 to the power minus 4 newtons. Right, so yeah, there we go. Let's move to the next question and see what we can do. So 7.4, let's draw a labeled vector diagram to show the directions of the electric fields at the point where X is positioned. Right, so in our question statement, we are told that a third point charge Z of unknown positive charge. So we have a positive right here, and then it is placed 0.01 meters to the left of point charge X on the line joining point charges X and Y, as we can clearly see. Right, so we need to draw a labeled vector diagram to show the directions of the electric field at the point where X is positioned, right? So let's say X is positioned somewhere here. We're gonna have an electric field as a consequence of our charge Z, right? So let's call it E1 pointing to the right, and then the electric field due to Y is gonna be to the left, right? So we have something like that for 7.4. 7.5, it says that the magnitude of the resultant electric field at the point where X is positioned is 4.91 times 10 to the 5 newtons per coulomb. Let's calculate the magnitude of charge Z. So the resultant electric field will be equals to E1 minus E2, right? As we can see that they are pointing in opposite directions. So E net is 4.91 times 10 to the power 5. And then E1, we don't have E1, right? That is what we're going to use to find the charge of Z. So we have E1 minus E2. So we're going to have K. Let's not forget that E is equals to K, Q divided by R squared, right? So we're going to have 9 times 10 to the power 9 multiplied by 7.2 times 10 to the minus 9 divided by the distance, right? From here to here is 0.03 squared. So we have is 0.03, right? So we're gonna have 0.03 squared, right? So we're gonna have 4.91 times 10 to the power 5 plus 9 times 10 to the power 9 multiplied by 7.2 times 10 to the minus 9, everything divided by 0.03 squared, and this will be equals to E1, right? So instead of writing E1, let's go ahead and substitute, right? So we're gonna have 4.91 times 10 to the power 5 plus 9 times 10 to the power 9 multiplied by 7.2 times 10 to the minus 9, everything divided by 0.03 squared, and then this will be equals to 9 times 10 to the power 9 multiplied by the charge of Z divided by the distance. So the distance from Z to X is 0.01 meters, right? So we're gonna have 0.01 meters, and we can square that. On the left hand side, I have 5.63 times 10 to the power 5. This is equals to 9 times 10 to the power 9 multiplied by the charge of Z divided by 0.01 squared, right? So the charge on Z will be equals to 5.63 times 10 to the power 5, everything divided by 9 times 10 to the power 9 divided by 0.01 squared, right? And then ultimately we're going to get 6.26 times 10 to the. Have you ever calculated the EMF using simultaneous equations? That's what we're going to do for this question, right? Look at 8.3. We have to calculate the EMF, but we don't have the internal resistance, right? But before we do that, let's do 8.2. So 8.2.1, we're looking for the reading on the voltmeter. So our voltmeter is connected across this 3 ohm resistor, right, as you can clearly see. So what you have to realize here is that the current splits at this point. So we have two parallel paths. These two resistors, the 2 and the 5, are parallel to the 3 ohm resistor. And then what do we know about resistors in parallel? We know that the voltage is the same, but the current is different, right? So to find the reading on the voltmeter, we can actually use this current we are given in A1 and multiply it by the resistance of these two resistors. We can find the VP by doing that, right? We know that if we do that, it's going to be the same value that is in the voltmeter, because the 3 ohm resistor is in parallel with the 2 and the 5 ohm resistor, right? So what are we saying? We're saying that we can have VP is equals to I multiplied by R. So VP will be equals to 1.5 multiplied by 7, right? Pretty much straightforward, no complications whatsoever. And then if you put that in a calculator, you should get 10.5. So the answer here for 8.2.1, we have 10.5 volts. That will be the reading on the voltmeter. Right, let's move forward and do 8.2.2. What are we looking for? We're looking for the reading on ammeter A2. So right, if we go to our sketch, you're gonna realize that ammeter A2 is here, right? So basically what we're looking for is the total current, because ammeter A2 experiences total current. So we're looking for IT. What do we have up to so far? We have VP, which is equals to 10.5 volts. What we're looking for is IT, right? But then we have a formula that says that VP is equals to IT multiplied by RP. So since we have VP, we can find RP, and then by doing that, we're going to ultimately find IT. So let's go ahead and find the resistance in parallel. We can say that 1 divided by RP is equals to 1 divided by R1 plus 1 divided by R2. So RP is equals to 1 divided by the total resistance on this path, which is 3 ohms, right? Plus 1 divided by the total resistance on this path, which is 2 plus 5. So we're supposed to have 2 plus 5 here to the power minus 1. And then if you put that in your calculator, you're going to get 2.1 ohms, right? So now we have RP. We can then say that VP is equals to IT multiplied by RP. So VP is 10.5, and then IT is what we're looking for. But what is RP? RP is 2.1. It's easy to see now that IT will be equals to 10.5 divided by 2.1, which is equals to 5 amperes. Right, so the value of IT is 5 amperes. Right, let's move to the following question. We're looking for the power dissipated in the 3 ohm resistor. So to determine power, there's quite a few formulas we can use. We can say that P is equals to V squared divided by R is equals to V multiplied by R by I, or it is equals to I squared multiplied by R. So let's see if we can use the first formula. We have the voltage, it is 10.5 volts, and then we have the resistance, which is 3. So we can use this formula. We don't have to try use any other thing. So we're gonna have P being equals to, what is the voltage? 10.5. And then we square that divided by the resistance, which is 3 ohms. Right. So now it's just a matter of putting that in your calculator. And then when I do that, what I'm getting 36.75. So I have 36.75 watts. Right, that is 8.2.3. The question we're really interested in is 8.3. So in 8.3, we're told that switch S1 is now open while switch S2 remains closed. The reading on the ammeter E2 is now 3.64 amperes. So when S1 is open, now we have an IT which is equals to 3.64 ampere. We have a total current which is equals to 3.64. So let's go to our sketch and see what happens when switch S1 is open. So when switch S1 is open, the current is no longer passing this point, right? So basically, all the current is gonna flow like this. All the current is gonna pass through the 3 ohm resistor, right? So now our total resistance is 3 ohm. So to calculate the EMF, we can say that EMF is equals to I multiplied by R plus the internal resistance. So our EMF will be equals to the current, which is 3.64, multiplied by the external resistance, which is 3 ohms, right, plus the internal resistance. So EMF is equals to, so we have 3.64 multiplied by 3, which will give us 10.92 plus 3.64 R. As you can see, we're looking for the EMF, but we don't have the internal resistance. So we're stuck. We have one equation and two variables. So we can call this equation 1 and go ahead and try find another equation so that we can solve simultaneously. So this is when IT is equals to 3.64 ampere. But what happens when IT is equals to 5 amperes? Like we had when both switch S1 and S2 are closed, right? So now we can use this information. We know that the corresponding current is 5 ampere, right? So we're going to say that EMF is equals to I multiplied by R plus internal resistance again. So the EMF is equals to the current, which is 5 amperes when both switches are closed, multiplied by the external resistance, which is RP, right? That was 2.1, and then plus internal resistance. So the EMF is equals to 10.5 plus 5R. Equation 2. So we can equate these two equations and determine the internal resistance and ultimately the EMF. So equation 2 is equals to equation 1. So what are we saying? We're saying that 10.5 plus 5R should be equals to 10.92 plus 3.64R. Right, so let's take 10.5 to the right hand side and take 3.64R to the left hand side. So if we take 3.64R to the left hand side, we're gonna get 1.36R, and then when we take 10.5 to the right hand side, we're gonna get 0.42. So R is equals to 0.4Q divided by 1.36, and that is equals to 0.31. Actually not 0.31 but 0.3088 ohms. Right, so we have the internal resistance. We can substitute it into either equation 1 or 2 to find our EMF. So if we substitute it in equation 2, we're gonna get 10.5 plus 5 multiplied by 0.3088. Right, so we have 10.5 plus 5 multiplied by 0.3088. I'm getting 12.044. So 12.044 volts seems to be our EMF. Right, and now this trick equation 8.4 is actually out of 4 marks. So what is it saying? We have switch S2 is now opened while switch S1 is closed. So let's go ahead and make that adjustment. S2 is now opened. So S2 is now opened. The 3 ohm resistor is no longer taking part in our circuit. We can essentially just erase this. Yeah, we no longer have that when switch S2 is now open. How does the voltmeter reading change? Actually, let's not erase it because now we cannot see our voltmeter. So let's just erase S2 alone. Let's just erase S2 alone. Right. Yeah. There we go. How does the voltmeter reading change? Choose from increase, decrease, or remain the same. So the voltmeter is reading V external, right? So what will happen to V external when that switch is open? The first thing to realize that R external increases. That's what's going to happen when that switch is open. R external is going to increase. But if R external increases, and we know that I is equals to V divided by R, then current decreases. If current decreases, and let me show you something, EMF is equals to I multiplied by R plus I multiplied by the internal resistance. If the current decreases and then our internal resistance stays the same, then V internal is going to decrease, right? V internal decreases. But we need the EMF to stay the same. So to combat a decrease in the internal potential difference, V external increases. So the answer that we're looking for here in 8.4 is actually increases, right? The reading on the voltmeter will increase